Hi, this is Thomas Vecca, and this is a tutorial for VCell version 5.1, an environment for modeling cell biological processes developed at the National Resource for Cell Analysis and Modeling at the University of Connecticut Health Center. It is funded by the NIH, and this is a tutorial for FRAP with binding. So, what we're going to do first is to select the structure tool, and we're going to create another compartment and membrane. And then we're going to choose C0 and change its name to site for cytosol. And then membrane 0 becomes NM for nuclear membrane, and then C1 can become nuke for nucleus. And so these are the only compartments we need, and now we can select the species tool and create the species. And for this model we need to create 6 within the nucleus region. So now we've created our 6 species, and we need to name them. So S0, its name is going to be R, and in the annotation field we will put RAN. And then for S1 it will become RF, and its annotation will be RAN FITC. And then S2 will become R capital B for RAN bound. And S3 will become capital B capital S for binding sites. And then S4 will become RF capital B for RAN FITC bound. And the final species will be our laser, which is our light source. And so now we've created and named all the compartments and species for this model, and we can head to the reaction diagram. And as you can see, our species are very clustered and hard to see, so with the select tool you can move them around, and as you move them, the nucleus column will become larger or wider, so you have a lot of freedom with how you want to move them. And for this particular reaction diagram, this setup works very well. And this one, I'm just gonna delete the S1 that didn't get overwritten the first time. And so now this is a good way to organize them, and now we can actually create the reactions. So we'll select the reaction connection tool, and then select the binding site and drag a line to the white space above it. And now we want to add R as a reactant in this reaction, so we'll drag from R to the new reaction icon. And their product is going to be RAN bound, so dragging from the reaction icon will connect the line to RAN bound. And then for the second binding reaction, this time we will drag from the binding site downward. Sometimes if you misclick, you'll accidentally create a new reaction, and then you can delete it. You have to delete the reaction first and then delete these species, and you can do that by clicking them and then pressing the backspace on your keyboard. And so select RF and drag to the reaction icon, and then we'll drag from the reaction icon to the new product RF bound. So these are our 2 binding reactions, and now we have 2 bleaching reactions to create. And with this one, for the bleaching reactions, we can select RF and then drag it to R. And this will create the reaction with RF as the reactant and R as the product. And then we can do the same over here. And now we can designate our laser as the catalyst for our 2 bleaching reactions. And now we need to specify our reactions and what type of reactions and the rates of them. So we'll select the first binding reaction, R0, and we'll change its name to RAN binding. And then its forward, we'll leave the kinetic type as mass action, and its forward rate constant will be 0.02, and its reverse rate constant will be 0.1. And now we can select the second binding reaction and change its name to RAN FITC binding. Leave its kinetic type as mass action as well, and just as the previous reaction, the forward rate constant is 0.02 and the reverse rate constant is 0.1. And now we can start working on our bleaching reactions. So we can change R2 to bleaching 1, and this one's its kinetic type will become general. And now we have to enter in reaction rate J. So if we double click in the expression box, we can enter in V max times RF times laser times T is greater than 1.0 ampersand ampersand T is less than 1.5. And since we introduced a new parameter Vmax, we have to define its value ourselves, and for this model its value is 50. And then the final reaction will become bleaching 2, and just as the first bleaching reaction, we set its kinetic type to general, and now we have to enter in the reaction rate, which for this one will be Vmax 2 times RF bound times laser times T is greater than 1.0 double ampersand T is less than 1.5. And then again, Vmax 2 is a new parameter, so we have to define it ourselves, and we will enter in 50. And so now we've completed the structure diagram and the reaction diagram, and that's all we have to do for our physiology, and now we can move on to the applications. So we'll select applications in the navigation tree, click add new and select deterministic. And then you can either double click in here or right click and rename to name this application. And for this one we can name it compartmental because it's going to be a compartmental application. And once we select our application, we'll be automatically taken to the geometry tab, and we want to be in structure mapping. And because this is a compartmental application, all of the regions we created in the physiology are linked to a single compartment in the geometry. And so we just have to edit the sizes of our regions. And for the cytosol, we enter 523.33, which is the volume of a cell with a 10 micrometer diameter. And for the nucleus, we enter 130.8325. And then the nuclear membrane becomes 26.1665. And now we can head to the specifications tab and set our initial conditions. The only ones we need to change are R, RF, and the binding sites. The rest we can leave at the default of 0. And so for R we're going to enter 5, for RF we also enter 5, and for binding sites we enter 20. At this point you may want to save your model, so you can go to save as, and you can enter in any name you want as long as it is a name not shared by any other model within the database. And if it is, it'll tell you and have you change the name to something else, so don't worry that it won't save. And so now we can go to the simulations tab, and we can select add new simulation, and you can leave its name as the default or change it to whatever you like. And then we can go to, with this simulation selected, we'll go to edit simulation, and we'll be brought to a parameters tab and a solver tab. And for this simulation we can leave the parameters as their default, we don't have to enter in a new one. And we can go straight to the solver tab. And for this you want to choose an integrator that's anything other than the default. So I'm going to choose this one, and we can leave the time bounds as is, and we're going to change the time step from 1 to 0.1. And then we can finalize it by selecting OK. And with the simulation still selected, we're going to click Run Simulation. And then you can view the running status of your simulation here. And once it's complete or you have results that are available, you can go to View Simulation Results. And this one should finish fairly quickly because it's a relatively simple model. And so now you can view the concentrations of the different species, and some of them, like the laser, won't change concentration because it's just light. And so you can also, if you want to view multiple species at the same time, how their concentrations change, such as RAN and RAN bound, you can control click to show more than one at the same time. And then if you would rather view it as a spreadsheet instead of a time plot, you can click the Show Data tool and view their concentrations at each output. And so this has been our first application, and now we can move on to the next one, our spatial application. And so we're going to go back to the navigation tree and select our compartmental application, right click and select Copy. And then we can change its name to spatial, and then we're going to go to the Geometry tab. And then instead of structure mapping, another important thing to notice is because we copied it from the first application, it retained the sizes that we entered. But since this is going to be a spatial application, we're going to go to Geometry Definition, and then Add Geometry, New, and we're going to select Analytic Equations 2 dimensions. And so we automatically are given a new subdomain, and this is going to become the site, this will represent the cytosol. And now we need to create a subdomain for the nucleus, so we're going to go to Add Subdomain, and we're going to change the shape to circle. And we can leave the center point as is, and then we'll change the radius to 10. And then we'll select Add New Subdomain, and we can change its name to nuke. And if you want to edit the expression for your subdomain manually, you can double click in the value box and do so. So now we've created the new subdomain, we just need to edit its size. So we'll go to, with the nuclear subdomain selected, we'll go to Edit Subdomain, and then for size in X and Y, it will enter in 22, and for the origin in X and Y, we enter -11. And then we'll select OK. And it should look something like this in the slice view. If you can't see the circle, have the nuclear subdomain selected, and then click Bring to Front, and you'll be able to see it. And so now we've created our geometry, we have to go back to structure mapping, and with the line tool, we have to map our compartments from the physiology to the new subdomains. So dragging a line from the site to the site, and then within the nuke, we drag it to the nuke. So now Virtual Cell knows which compartment from here matches up with which subdomain we've created. And so now if we head over to specifications, we can see that their initial conditions have been carried over from the previous application as well. And because this is a spatial model, we also have an added diffusion constant. But what we want to do is we want to use the final concentrations from the compartmental application as our initial conditions for this application. So we'll go back to our compartmental application, go to the Simulations tab, select our previous simulation, and view its results. And this is where the spreadsheet tool comes in handy. And so we want to, using control clicking, you want to select our binding site, our RAN bound and our RAN RAN FITC and RAN FITC bound. And so it'll show the the concentrations of all those species, and we want to highlight the final concentrations of each species, and then right click and select copy. And now we can exit out of here and return to the spatial application and go back to the specifications, and then right click in the initial conditions column and select paste all, and then check select all, and as you can see, it's going to change the default initial conditions to the new ones that we copied. So then select OK, and now the only thing left is we have to define the initial condition of our laser. And what this equation will do, which is x is greater than negative 5.0 double ampersand x is less than 5.0 double ampersand y is greater than negative 5.0 double ampersand y is less than 5.0. And what this does, it restricts the activity of the laser to a rectangular area within the nucleus. And then, because we have reactions in this spatial application, we can check the reactions tab, and we want to make sure all of our reactions are enabled. And we don't have to check any of them as fast, because no single reaction is much faster than any other reaction. So none of them are fast in comparison to each other. And now we can head to the Simulations tab, and we can take this simulation and we can go straight to editing it. Nope. So if that happens, we go to Generated Math. If there's ever an error that won't let you edit your simulation, it's because it hasn't been saved, so the math hasn't been updated. So if we go to Generated Math and then select Refresh Math, it will make sure it will update the math of your model. And now we can edit our simulation. And because this is a spatial application with that geometry that we've created, we also have access to the Mesh tab. And we do not have to change any of the default parameters, and we can head straight to the Mesh tab. And we want to make sure lock aspect ratio is checked, and enter in 51 for x. And what lock aspect ratio does is as you change the value for one coordinate, it adjusts the other ones accordingly. And now we can head to the Solver tab, and we can leave the integrator as the default fully implicit finite volume regular grid, and then we can change the ending time to 50 seconds and change the output interval from 0.05 seconds to 0.5, and then we'll select OK, and then we'll run our simulation. And then again, you can view the running status, and once it's completed or you have results that are generated and it's still running, you can select view simulation results. So it's completed, and now we'll select our simulation and choose to view the results. And now we have an actual diagram because we've created the geometry, and we can choose to view it in grayscale, concentration, or blue-red. And whenever you're viewing the concentration gradients, it's always important to note the max and min, because as you can see, these don't start differing until here, which is a relatively small difference, but you could run a different simulation and get a difference that starts within the tenths, and it will still have the same color scheme. So it's always important to check your maximum, minimum, and minimum values. And you can move through your time steps using the slider here, and you can view the concentrations of different species by selecting them here. And then if you want to create a spatial plot of your data, you can use the line tool or the spline tool to designate a region. But if you want to make a time plot, you can select the point tool and choose points one or more than one, however many you want, wherever you want, and then you can plot them as a time plot, which basically functions the same way. It expresses the data similarly to the plot from the compartmental model, and you can change which species you want to view the concentrations of, and then as before you can also view it as a spreadsheet. And that's the end of the FRAP with binding tutorial.